Hey everyone. So let's talk about the absolute foundation of physics. If physics is the story of the universe, then units and measurement, that's its alphabet and grammar. Seriously, if you get this right, everything else just clicks into place. Today, we're going to dive into the core ideas that won't just help you ace your exams, they'll get you speaking the language of science like a pro.
All right, so here's our game plan. We're going to start with why we even need a common language in physics. Then we'll get into what that language actually is, the SI system. From there, we'll tackle the grammar, significant figures. And then I'll show you a superpower for checking your equations. We'll wrap it all up with a toolkit you can take with you. Sound good? Let's jump in.
Okay, so first things first. Why does any of this even matter? Well, think about it. In physics, you can't just say the car is fast. What does that even mean? Is it fast like a cheetah or fast like a rocket? To get a real answer, you need numbers. Physics is all about measuring things. It's a quantitative science, and that's where we have to start. Just imagine this for a second. You're building a rocket with a team, but your definition of a foot is totally different from your partner's. It would be an absolute disaster, right? Total chaos. And that's the core problem we're trying to solve. How do we create a system that's so universal that a measurement made in Tokyo means the exact same thing in Toronto, no questions asked?
And the solution is actually this really simple but powerful idea. At its heart, measurement is just a comparison. That's it. When we say a table is 2 meters long, all we're really saying is that it's 2 times as long as this standard thing we've all agreed to call a meter. See? And that means every single measurement has to have 2 parts, the number and the unit. If you forget one of them, the whole thing is completely meaningless.
So to avoid all that potential chaos, the scientific community all over the world got together and agreed on a single set of standards. This is where we get to meet the basic building blocks of all measurement, what we call physical quantities, and the brilliant system that ties them all together, the SI system.
In physics, we basically have 2 types of quantities. I want you to think of the fundamental quantities as our alphabet. These are the basic independent letters like length, mass, and time. Then you have derived quantities. These are the words we build using our alphabet. A great example is velocity. It's not fundamental. It's just length divided by time.
And here they are. This is it. The entire alphabet we need to describe the whole physical world. It's called the International System of Units, or just SI for short. And get this, there are only 7 base units. Just 7. From the tiniest atom to the biggest galaxy, everything, and I mean everything, can be described with some mix of these 7. You master these, and you are officially speaking the universal language of science.
Okay, so we've got our language down. Now we need to learn the grammar. And in the world of measurement, grammar is all about precision. This brings us to a topic that, let's be honest, trips up a lot of students: significant figures. But trust me, once you get this right, your accuracy is just going to skyrocket.
So, what in the world are sig figs anyway? The best way to think about them is as honesty in numbers. That's really what they are. They tell you, and anyone else looking at your work, just how precise your measurement actually is. It's basically all the digits you're totally sure about, plus that one last digit that you had to kind of estimate. Now, there are a few rules you gotta know to master this. Rule 1, super easy. If a digit isn't a 0, it's significant. Done. Rule 2, if you see a 0 that's sandwiched between other non-zero numbers, like the 0 in 101, it's always significant. It's part of the measurement. Now, rule 3 is the one that gets people. Those leading zeros, the ones at the very front of a number, like in 0.052, they are not significant. They're just placeholders. Their only job is to show you where the decimal point is.
Okay, now look at a number like this. This is roughly the diameter of the Earth in meters. Writing out all those zeros is just tedious. But more importantly, it's kind of ambiguous, isn't it? Like, how precise is that measurement really? It's hard to tell. There has to be a better way to write this.
And of course there is. Here's the super elegant solution. Scientific notation. Look at that. It instantly cleans up the number. But the most important part is that it removes all the doubt. Right away, you can see this measurement has 3 significant figures: 1, 2, and 8. There's no ambiguity, which is exactly what we're aiming for in science.
All right, now for my favorite part. Seriously, this next technique is like a cheat code for physics exams. It is your secret weapon for checking if your equations even make sense before you waste time plugging in a single number. I am talking about dimensional analysis.
And the idea behind it is just beautifully simple. Here it is. Any equation that's actually valid in physics
must be dimensionally consistent. What does that mean? It just means the dimensions on the left side of the equal sign have to be the exact same as the dimensions on the right side. You can't have apples equal oranges, and you can't have length equal time. It just doesn't make sense.
So how do we do it? We use a really simple code. We use m for mass, l for length, and t for time. Pretty much everything can be broken down into some combination of these three. So velocity, that's just length divided by time, so its dimensional formula is lt to the -1. Force, well, that's mass times acceleration, which breaks all the way down to mlt to the -2. See? It's a system.
Okay, let's put this superpower to the test right now. Here's a famous formula, the one for the time period of a simple pendulum. So t is the time it takes to swing, L is the length of the string, and g is the acceleration due to gravity. The big question is this formula dimensionally correct? Let's find out. All right, let's start with the easy part, the left-hand side of the equation. It's just t for time period, so its dimension is simply time. We write that as t. That's our target. The right side has to match that.
Okay, now for the right-hand side. First off, we can just ignore the 2 pi. It's just a number, it has no dimensions. So we're looking at the square root of L over g. Dimensionally, that's the square root of length, L, divided by acceleration, which is Lt to the -2. Now watch this. The L's on the top and bottom, they cancel out. So now we're just left with the square root of 1 over t to the -2. And that simplifies to the square root of t squared. And what's the square root of t squared? It's just t. And there you have it. The left side is t and the right side boils down to t. They match perfectly. We just proved that this formula makes physical sense without using a single number. That right there is the power of dimensional analysis. It's such an incredible tool for checking your work, especially in an exam. All right, so let's bring it all home. Let's wrap this up and pack your foundational toolkit with the absolute must-knows from today.
So why does all this stuff matter so much? Look, this is way more than just about passing a test. This is about building the solid, unshakable foundation for your entire journey into physics and science. It's about being confident that your experiments are accurate, that your equations are actually valid, and knowing that you are speaking the very same language as every scientist who has ever made a discovery.
So I'm going to leave you with this thought. You now have this incredibly powerful toolkit to question and really interrogate the physical world around you. So the next time you see a physical law or an equation in a textbook, don't just blindly accept it. Challenge it. Put it to the dimensional test yourself. The only question left is, what will you test first?